by thanking the organizers for the invitation to give a talk at this meeting. In particular, my thanks to Amit and also to Dipali, who played a major role in getting me here. In particular, she had to work very hard during one weekend to try to get a letter of invitation for me because the agency that handles this visa application is in London didn't like the fact that the initial letter of invitation was addressed to me and not to the High Commission of India. So I don't know what she did, but definitely my thanks to her and to Amit that they were both involved in sorting this out. I hear though that Chris Jones was not that lucky, so anyway, I won't go into that. Right. So the plan is to try to give you some sort of bridge, as I see it, between sort of theoretical filtering theory and practical data assimilation. And in some sense, as it was mentioned earlier by Alberto, in some sense you will see that the talk of Professor Karandikar and Alberto's talk, I mean, there's a lot of overlap between them. And this is one of the things that I'm trying to see. I'm trying to sort of make aware the community that does data assimilation of what's been happening in filtering theory and vice versa. Having said that, I'm nowhere near an expert in data assimilation. Particle filters, for the moment, are seen as sort of some sort of theoretical, as a sort of towards the more theoretical side of the data assimilation, and there's still a lot of reluctance to apply particle filters. My work within the particle filtering area is theoretical. So I'm on the theoretical side of the data assimilation. So if you find what I'm saying very theoretical, you'll know why. But I will try. I'll do my best to try to explain things in a language that hopefully will make sense to people that are really applying these things, to people that are working data assimilation. But I will not be able to perhaps answer all the questions that are coming from practice that are amazing questions. And I have been very much motivated in the last 2 years by the variety of practical questions that are coming from data assimilation to try to see if theoretical particle filtering can help with that. And because before I begin, let me just say that I've been very, very keen to do that. And in Britain, we will start a new center that has at heart geophysical sciences and research in the area of weather and climate. And we will start in September this year. We have funding for this. And obviously, data assimilation will play a very important role in this, and I will play an important part in this. And I'm hoping that at least some of the participants of this workshop will be able to visit our center and be able to interact with members of this center. So this is just to show you that I'm really very keen on data assimilation and in particular in its application to geophysical sciences. So what do I plan to do? This is what I plan to do for throughout the course. So today, my intention is to establish a vocabulary to try to tell you, on one hand, what stochastic filtering is, and I will use the discrete version of the framework. Professor Karandekar presented the continuous version of the framework. The discrete version of the framework is the one that I choose because it's the one that's in many ways closer to data assimilation, to how researchers in the data assimilation see things. If I have time, I will point out from time to time, what's happening in continuous time. Why what are the difference for the continuous time framework. I have to say that most of my work is in continuous time. So this is just part of my work. But this is the bridge. Here is where basically I think the interface between data assimilations and filtering is, filtering in discrete time is the bridge. So in this manner, I will give you the Bayesian formulation of data assimilation. Alberto said something about what data assimilation is. I will try to, in some sense, rephrase what he says and set up a stable framework on which, hopefully, we can engage and establish a dialogue. And the one thing that is in many ways in common to both stochastic filtering and data assimilation is the numerical part. And in the numerical part, both topics, both subjects have the same interest at heart. We are interested in processing data, having some sort of initial belief, having some model which may or may not be correct. And this data is processed by means of algorithms. And the point that I will make is that, in some sense, particle filters and ensemble-based algorithms are one and the same thing. And I will home in on particle filters towards the end of the lecture today, and so that basically I establish kind of what's going to happen next. But today I will not give you a lot of details. I'll just sort of give you a flavor of what particle filters are. Tomorrow is going to be, we have a different story. So tomorrow I'm going to go back to the framework that I will talk about today, and I give you a lot more details. And the reason why I give you a lot more details is because, based on these details, I will be able to establish a theoretical result which I think is quite important, which I think can be applied not just to particle filters, but to any algorithms that are out there that solve either a stochastic filtering problem or a data assimilation problem. So the aim tomorrow is going to be to prove a theorem which is going to be a necessary and sufficient condition for the convergence of a certain algorithm. So for this, I will spend some time going over the base formula for the conditional distribution of the signal, trying to sort of get you accustomed, if not with the theory, but at least with the notation for the base formula. And then I will state and give you almost a complete proof of this theorem that basically will tell you what you need to satisfy so that you have a convergence of a particular algorithm. So this what's going to happen tomorrow, in some sense, is independent of the framework, is independent of both particle filters or an ensemble-based algorithm. the theorem is simply going to say that if you want to have convergence of a certain approximation to the posterior, and it's going to be up to you what you want to, what your approximation is, then you have to satisfy certain constraints. But I'm not going to say this approximation is a particle filter, and I'm not going to say that this approximation will be, I don't know, a sort of anything based on wavelets or anything, or sort of Gaussian interpolation or anything like that. It's a very general theorem, and I'm hoping that once you see this theorem, and I'm hoping to convince you it's not a difficult theorem to apply, you will be minded so that when you look at approximation, even when you work in data assimilation, you will try to see whether the conditions of the theorem are satisfied, and therefore you would have some sort of convergence. And this is not day 2; it should be day 3. I need to make that correction. So the day after tomorrow, I'll go back and I will spend time on particle filters. I will give you details of how you construct a particle filter, and show you how you can apply the theorem that I will prove tomorrow to particle filters, and therefore show you that particle filters are theoretically justified in the sense that as you increase the computational effort, in this case the computational effort will be approximated, or in terms of the number of particles in the ensemble, then you have the convergence to the real probability distribution, to the posterior distribution. So that's what's going to happen on Friday. And then I'll have, towards the end, a very short addendum on why data assimilation is difficult. And obviously the reason is because we are dealing with high-dimensional problems, as we heard earlier on. The dimension of the state is 10 to the power 9, very, very high. And so typically a particle filter means that you have a combination of particles, a cluster of particles. Each one of these particles will take values in a state. So we'll have to have 10 to the power 9 dimensions. So it's quite hard to envisage at this point in time an approximation that has a million and million of particles, each one of them having evolving in dimension 10 to the power 9. Once I tell you that, I will also show you an application, and this is our toy model. Everybody talked about toy model, and there was the question earlier, what is a toy model? And the application that we have So we have an application to the observed. So this is the partially observed Navier-Stokes equation on the torus. And I'm going to give you just the numbers. The numbers are the state space. So the signal. We work with the Navier-Stokes in Fourier mode, and in Fourier mode we have 64 square modes, and obviously Navier-Stokes is velocity, so we have 2 dimensions for each of these. So it's so the signal is about 9,000. So that's the dimension of our toy model. Nowhere near 10 to the power 9, but anyway, a lot more than a one-dimensional model. And the observations are sparse. The observations are sparse, similar to the one that you saw earlier for the Indian Oceans. We have a grid, a physical grid of 4 by 4 grid. I'm just going to show you the grid. Let's hope I can access the Dropbox in real time. So, So the grid is made out of this 4 by 4. It's gone now. Let me see if I can stop it. So the observations are the value of the equation at these 16 points. So it's 4 by 4, and of course each one of them is, the actual solution is this one. This is the vorticity. So this is the solution of the Navier-Stokes. You observe the velocity of these 16 points. So you have 2 dimensions for each one of them, and we incorporate 5 sets of data. So our toy model has this much. So in some sense, the size of the observations is similar to the size of the model that was presented earlier, but the problem is the signal. We are still nowhere near 10 to the power 6, I think it was. But yeah. We incorporate, we measure the velocity at 5 different times. And the velocity is measured. It's a regular grid, homogeneous in space. The size of the fact that the grid is regular or not plays no role in the amount of computation. Right. So this is the observation. We use in here 1,000 particles, right? So we think that's more than enough to get an accurate approximation, as opposed to the 50 that were in the example that you had before, and it takes 7.5 hours. So we are off the low-dimensional case. We are still a long way away from the 10 to the power 6 or 10 to the power 9, but we are on the way. We are on the way, and we have just started. And there's lots of things that we need to do to get there. The point that I'm trying to make is that this is very promising, and I would invite people that apply these things to look into this area. Okay, so I'm going to give you more details on Friday, but I thought I should whet your appetite and tell you about this. And just in case I don't care to talk about this, my flight is at 7 o'clock. I may have to leave very quickly, so have a look at this. If I can not talk about this. Right, so let me try and get back to today's talk. If you have questions, do ask questions. There's no problem. I am not restricted by 1 hour. I have 3 hours, so I'm happy to answer questions. I should point out that I gave, Chris Jones and I gave a talk not dissimilar to this one at Oberwolfach 2 years ago. And don't be scared that I have to go through 65 pages. I don't need to go through 65 pages. In particular, 2 years ago, in my talk in Oberwolfach, I managed to cover just 8 pages. So there's and Chris Jones covered even less. I think he was stopped at page 2 or something. So yeah, I'm sorry he cannot be here. He could tell you a lot more funny stories about that session in Overwolfa. But anyway, go on, Alberto. What did you want to?
Well, it's again about this example. So 7.5 hours.
Yeah. So what we had before, we had an inverse problem. We wanted to get the initial conditions, and the amount of time that it took to assimilate this data to get to an accurate estimate of the posterior of the initial condition was 7.5 hours. 1,000 particles, yeah. Yeah. Go on. No. So how did we know that we got it right? We used obviously MCMC. Okay. So I'm just going to show you. I'm happy to show you this. You know, in case I don't get to. So this was the true initial condition was sampled. It was random and was a sample from a normal in that dimension. And this is what we get by using our particle filter, and this is what you get by doing the MCMC. So the only way in which we could validate our results was to compare it with the MCMC. Now the MCMC to do the MCMC to incorporate this, to assimilate this data, it took 9 days. MCMC is very expensive. It took 9 days. Sorry, 7.4 hours. So I was wrong. So to do our particle filters to incorporate the same amount of data, it took 7.4 hours. So this was an inverse problem. We were estimating the initial condition with no noise. There was no noise in the model.
So this means, again, I would say, that if you change by using the same amount of observation, and you change the distribution, the spatial distribution, by making a denser observation when the flow grows faster, or vice versa, this convergence should happen faster. So
we don't know. We don't know. So if in order to justify what you just said, we would have to run the MCMC and run the SMC and see if you get it. Right? This is the only way. We don't have the answer. We don't know what the actual posterior is, and the only way in which we can find this out is to do the MCMC. Now, unfortunately, if you put more and more observations, the MCMC takes longer. Go on. This was the best that we could do in December 2012. This is, yeah. Okay? Right. So, okay, so let me just now go back to today. Yeah.
What is the distinction between filtering and smoothing and data assimilation? I understand.
I'll get there.
High dimensionality.
I'll get there. The answer is, I want to try. My point is there's no difference. So I want to say that these are two communities that are trying to solve the same problem, and there is a language barrier here. But other than that, there should be a lot of interaction between the two. And what Amit has been doing with this workshop is exactly this, trying to build up a bridge between the two communities. Filtering is a very old subject. It's started, I'll say, with the work of Wiener, Kolmogorov, and it continued through the Second World War, through the work of a lot of people that are here. The Indian school played an important role in the theoretical development of filtering theory, and it is the case that somehow the fact that this bridge, people are working on this bridge here in India, it's not surprising because, India is one of the, like a good house, a good place for filtering. Not just India, but some other countries. But India plays a very important role in the theoretical development of filtering theory. So a lot of people have worked in this area, and we heard earlier names like Kalyanpur. Of course, Professor Mitter has worked on this. Professor Karandikar. And we have a whole variety of people from India that worked on this subject, on the theoretical development of this subject. And I cannot stop but make this comment that I wrote a book on the theoretical development of filtering, and this book had in the introduction, it had a sort of historical account of filtering theory, and which, to the best of my ability, I tried to explain how the various developments came about and how they were related. And I can tell you that the most feedback that I got was not from the book, but from the historical account. I received maybe 90% of the emails that I received about the book were on how wrong I was with the historical account, that this theorem or that theorem should be addressed to this person, not to that person, and so on. If you get to look at the book and look at the historical account, please do not send me an email. I promise to everybody that I'll take this out if there is going to be a second edition. Right. So anyway, so what I want to do now is basically mirror what Professor Karandikar presented earlier today, and just give you briefly the description of the filtering problem, this time in discrete time. And this is going to be short, but tomorrow I'll come back to this and I flesh it out with all the details required, so that I am able to prove this fundamental theorem, fundamental convergence theorem. So the filtering is a game of two halves, if you want. The first half is a dynamical system which is modeled by a process, which you call the signal process. And this is the component which is not directly observable. So in statistics, it's also called the hidden component. And it's your weather, the state of your atmosphere, if you want, in data assimilation, or the temperature of the oceans, or something like that. So that's your model, if you want. And then you have an associated process which models your data, the data that you receive. Right. So I think it's Control L. So this is called the observation process, and for the purpose of this talk, I'm gonna assume that the data is a function of the signal at the current time and some noise. And I'll make this very specific as we go along. For the moment, that's take it as it is, very abstract. There are a lot more general frameworks than that, where the observation can depend on the entire trajectory. We can have some sort of averaging of the signal and so on. I'm not going to go into that. I'm just going to stay with this. And in fact, I'm going to stay with something which is even more concrete than this abstract definition of the observation process. So we have these two processes. One is the signal, the other one is the observation. We have the observation, we don't have the signal. We want to get to the signal just by using the observation. So that's this is the filtering problem. Basically says you have all this observation and t here. I'm putting it like this, but think of t being discrete. I'm going to make it clearly in a minute that t is discrete. T is 1, 2, 3, and so on. So have all the observation y1, y2 up to yt up to the current time, right? And you want to estimate the position of the signal at time t given your observation. You want to estimate given the position of the signal at time t given your observation. And if you want to make this very, very rigorous and put it in mathematical terms, you want to compute the distribution of the signal at time t given the observation filtration. And I'm going to denote this by pi t. And I make the point that in data assimilation, people do the same thing. You know, in the ideal world, if we will have no error and we would have no impurities and the Earth will be perfectly spheric, in an ideal world, that's what you want to get to. You want to get to the conditional distribution of the signal given the observation. But we don't live in an ideal world, and so the best that we could do, we could just get an approximation of this, right? So in data assimilation, people say we want to find a way to incorporate the observation into the model. That's the sentence that is used, and that simply means that we want to try to estimate the signal given the observation. So the language is different, but people want the same thing, right? In data assimilation, people, because the dimension of the space is so big, you can never hope to get the posterior distribution, right? So rather than say, what's the point in sort of trying to say that we're going to get to the posterior distribution, the actual posterior distribution, you just want to say, we want to find a way in which you incorporate the observations into the model. You want to find a way in which you estimate the model given the observation. So the point that I'm trying to say is that we are looking at the same problem. And some people, they call it stochastic filtering, and some people, they call it data assimilation. Now, smoothing, what is smoothing? And this was mentioned earlier. Smoothing is, so you are not interested in estimating the position of the signal time at the current time. You are interested in computing the position of the signal at time 0. That's what I'm going to do. That's what I did here with this moving. Conceptually, there's no difference between the two. In some sense, you can still think of it as a filtering problem, but the filtering problem on the path space. So smoothing is, in some sense, doing filtering on the path space. That's all, right? So I'm not going to go more into that, but I just want to clarify this. What is the difference between smoothing and filtering? Now, smoothing can be also interpreted as an inverse problem, and so on. I'm not going to go into that. OK, so the two communities have at heart the same problem, but they look at the same problem in different ways. OK? Now, I'm going to establish the frameworks. I have to tell you about the frameworks. I'm going to tell you about the framework very quickly, but before I go into formulas, I'm just going to show you this picture, right? Because I think this picture is very helpful to actually see what's going on, and so regardless of whether you work in filtering or data assimilation, these pictures will make sense for all of us. So imagine. So this is one trajectory of the signal. This is the truth. This is the signal there in the state space. And the state space here can be very high. We looked at the problem earlier. It was 10 to the power 10 to the power 6. It could be 10 to the power 9 if you take all variables into account. So this is the evolution of your ocean, Indian Ocean, in this high-dimensional space, or the evolution of the entire atmospheric, the evolution of the atmosphere. So this is what we look. We don't have direct information about this. We cannot measure this, but we have some partial information. So what you have, you have some observations, which are some functions of the state, some functions of your model, some functions of your Indian Ocean position, or some function of your atmosphere, noisy ones. There's noise. Okay. So for example, in this case, this was H was what? You were just looking at the projection on this sparse grid. That was your H, right? The projection on the sparse grid, and we had some noise added to them because, for practical reasons, it's we don't really believe that our measurement instruments, the accuracy of measuring the velocity of the air at a particular point is 100%. So you put some noise into this. Okay, so now I'm going to make the connection to what Professor Karandikar presented earlier. What you saw earlier, you saw this equation. So this is the continuous time version of this. In continuous time, it makes sense to say that you pretend you observe not this but the integral of this, and as a result, the equation for your observation process looks like this. It's an integral of some function of x to which you add Brownian motion, which is the right thing to add, the right continuous time version of the integrated white noise. So these are the two halves. One half is the signal. I'm going to come back to the signal and tell you about the signal. What is the signal? How does the signal evolve? And then the other half is the observation, which evolves in this observation space here. So the dimension of this guy is totally different from the dimension of this guy. Typically, the dimension of this guy is a lot smaller. Okay? So we know in here, that was the dimension, and you saw earlier that the dimension could have been even smaller than that. Okay? Right. So these are the two halves. So what you want to do, you want to get to the signal. Okay? You want to get to the signal. So how do you want to get to the signal? You want to get a grasp of the conditional distribution of the signal given the observation. The conditional distribution of the signal given the observation. Okay? So this is something that also Professor Karandikar pointed out earlier. So the way in which I wanted to visualize this, think of this as this. You have these blobs in here, right? So the way to think about this, think about this as sort of a probability measure, right? Which sits on this state space. So this is a probability measure, which the filtering problem doesn't really care about that in the first instance. So in the first instance, what you want to do, you want to estimate this blob in here. So this blob is evolving. Why is this blob evolving? Well, it's evolving because of two reasons. One is because the signal is evolving. The prior distribution is evolving. And the other one is because I keep getting information. I keep getting observation. So I have two sources. So this blob is evolving as a result of two sources. So one is because the signal is evolving, so it's pushed away, it's pushed away by the prior distribution, but also is evolving because I get more and more observation. Now we had this discussion earlier. Is it the case that somehow I get to the signal? In other words, is it the case that my blob gets smaller and smaller and smaller so that eventually I get to the signal? And the answer is unfortunately no, right? Because as you go along, you have more and more going. The blob is a distribution. It is a probability measure. I don't have a way to. Okay, right. So I'm going to come back to this, but think of it like that. It's not really the case, right? But for practical purposes, it is the case. So if you think of this as being a Gaussian distribution, of course, the support of the Gaussian distribution is the entire space. But for practical purposes, if you go more than 3 standard deviation away, you get 0. There's nothing there. There's no mass there. Numerics, if you implement it, your C program is going to give you 0. So, it's this thing that's a normal distribution. on one hand, you think of it as being having a support everywhere, but in fact it doesn't. It really is a very compact, you know, it has compact support there, right? So that's why I put a blob rather than trying to say it's the whole space, okay?
Am I getting kind of all probable trajectories of X with this distribution?
Okay, so that's a very fine question. Okay, so the reason why the reason why it's fine is that somehow this blob in here tells you what happens with the distribution at that time, t. Okay. Now, if you want to see what happens with the entire trajectory, with the whole path, you'll have to put together all these blobs, but you have to put together all these blobs in the right way because they are correlated. But if you put together all these blobs in the right way, with the right correlation, then you get the posterior distribution of the entire trajectories. In other words, you see all the trajectories in some sense, but you don't see them, you know, you just see them from the point of view of, from a probabilistic point of view, you can say something about where they lie probabilistically. Does that answer your question? Sort of.
So if you solve the filtering problem only, then you don't see the full trajectory.
No. You have the smoothing problem, then you see the whole trajectory. So if you solve the smoothing problem in the way in which was presented, who presented it? You presented it. If you solve the smoothing problem in the way in which it was presented by Alberto, then you see the whole thing. You see all the trajectories. Of course, it's impossible, and I'll make the point why it's impossible, because, you know, the dimension of the space is gazillions. But if you want to, you know, to answer your question, you have to solve the smoothing problem.
But you could go from the path estimations to filter by margin.
Yes. Yes. So if you have solved the smoothing problem, to get the filtering problem, you have just to marginalize on the latest thing.
Slightly digressing, how is this different from this least action principles that you were studying?
You mean the thing that Sebastian Reich is doing? Is it the thing that Sebastian Reich is doing?
Like,
Oh, least action filter. Oh, this is the guy from Cambridge. I forgot to. I'll explain in the break. Okay? It's different. It's very different. This is rigorous. That thing is not rigorous. That's one thing. Okay. Sorry? Sorry? How is this different from the least action filter? Least action filter. And I'll you know, we can.
Slides by Chris Rogers.
Yes, yes. So Chris Rogers. Yeah. Well, so there's a lot of connection. There's something that Chris Rogers has suggested. This is rigorous. There's 50 years of, 100 years of, many years of development in filtering theory, which makes it rigorous. I mean, even before that, it was, it's based on filtering, based on statistics. This thing is just something that he's been trying to do, using some ideas that are not quite kosher. That I don't know. That I don't want to go into that. Right. Right. I don't want to go into the connection between 4D-var in this one. Okay. Right. Go on. Yes. Yes. So the point I'm going to make is that because of the fact that particle filters will give you an estimation of the blob, which means what? You can come and tell me, I don't care about anything else but the signal. Okay, if you just care about that, I'll give you the conditional mean, which means I'm going to average over all my blob. I'll give you the conditional mean and I say, okay, this is the estimation of the signal. It's the conditional distribution, the conditional mean, the expected value of the signal given the observation. I'm going to tell you this is the best you can have given the observation, because there's a very simple mathematical theorem which says that the conditional expectation of the observation, the conditional expectation of the signal is the best estimate in some sense, but I can give you more. I can give you the covariance matrix, so you will be able to plot your, the whole probability measure. You will be plot your mean and quartiles and everything you want. That thing encompasses all the information that you may need, right? So that's why it's important. So, as opposed to just getting one estimate, this gives you everything. Of course, it's because of this. It's expensive, but you get everything, right? The question is, how can you make it less expensive? And this, there's lots of things that you can apply here. Dimension reduction, so we're going to hear about dimension reduction and all these other things which can come into being. The point is the blob gives you everything. Okay? Shall I go to page 3? Good. Oh, I'm on page 3. Ah, that's it. I can go home. Right. Okay, so now maths. Now I have to give you I have to flesh out a little bit on the model. So what is the signal? So the signal, I've shown you the signal on the previous page, adjusted trajectory. The signal is going to be a Markov chain. Okay? So I'm assuming that I have a random initial condition. So the initial condition of the signal, the initial position of the signal is random. It's sort of has a particular distribution, and I'm going to denote this particular distribution by pi naught, and then it's going to become apparent why I denoted pi naught in a little bit. So the initial condition, I don't know where my atmosphere is at time 0. I can have some climatological data. I can get some model for my prior distribution at time 0, but I will never know for sure where I am. So that's why I start from somewhere which is random. And then I'm going to assume that my evolution is a Markov chain. So that means what? That means that I know where I get to from time t minus 1 to t, and this is given by a transition kernel. Okay, so this transition kernel tells me where do I get probabilistically from, if I am at time t minus 1 at xt minus 1, it gives me the distribution of xt, of the signal at time t. So this is a transition kernel. And I'm going to come back to this transition kernel. I'm going to tell you what the transition kernel is and so on. So for the moment, just take it as it is. Now, a particular example, so a very simple example. So I'm just going to refer to this, the sort of the toy of the toy model, the toy model of the toy model. So for example, if you are just in dimension 1, right? So in dimension 1, so a particular Markov chain which you could take, and if you don't like working with this Markov chain, having in mind this Markov chain, because this is kind of the thing that if you work in data assimilation, you've seen again and again and again and again. So think of this, your signal as being x at time t is a function of x at time t minus 1 plus some noise, and you can think of it as just adding, say, a normal a random variable, which is normal mean 0 variance 1. Okay. Now, why do I want to add noise? Well, I want to add noise. There's several reasons why I want to add noise. Maybe that noise is already there in the evolution of my my signal. So think of, if your application would be, you look at the satellite or you look at an airplane, you have noise. The airplane is really blown, of course, by wind, by hitting, I don't know, small particles and so on. So there isn't a deterministic trajectory of your signal. So that's one reason why you should have noise in there. The second reason is maybe you don't really believe the model, right? So the model is your B in here. That's the function, and that's in my case it was Navier-Stokes, but maybe you don't really believe that Navier-Stokes was the right thing, and we've heard earlier that it's not really the right thing if you are close to the ground or up there or close to the ice sheet. That's not really Navier-Stokes. So we put a bit of noise in there. So why do you put noise in there? Well, you put noise in there because to allow for the possibility that maybe you are wrong, and in fact you don't go in the direction, in that one direction that is dictated by the B, maybe you go in a different direction. And by adding this noise, you allow for perturbation. You allow for possible perturbation to your model, which might not be perfect. Now, it may be that this B depends on the parameter. So you can have models where you say, okay, I'm not sure what the model is, but I think it's one of these, 3 models, 1,000 models, and so on. So I may have some cluster models that you can choose from, and then maybe you're going to say, okay, so which of these many models can I choose them? So in that case, you can expand your signal to put the parameters as part of the signal, and as you go along, you can go on and estimate not just the signal, but the parameter as well, right? So this is a separate line of research, very, very hard line of research, but very important one. But for the moment, for the purpose of this course, I'm going to assume that I know this B, and even if I don't know the B, somehow the fact that I don't really know B is hidden in a way in the fact that I take a random perturbation of BF XTI to give me XT. Now, an even simpler case of this is when B is 0. So what I'm going to tell you now applies to the case when I don't have any noise at all, right? So there's not going to be, the framework really applies to this case. I mean, in this case, the trajectory is deterministic. It is a Markov chain. It's a deterministic. Is a it's a very simple Markov chain, but that is covered. And this is just to say that the Navier-Stokes that we the application there, we didn't have any noise in that thing. Okay, so if you are happy with this, then think of it as think of the evolution of the signal like this, but to use my language, and you'll see why it's important to use my language. The corresponding transition kernel to this thing is given by this formula, right? So basically, the fact that you know where xt minus 1 is, then xt is just normal with mean given by this and variance and a half. So that's the transition kernel. Okay, and you'll see why it's better to work with this transition kernel. It makes life a lot easier when I get to prove my theorem. So for practical purposes, when I go and do my particle filters, it makes no difference between using one and another, no difference whatsoever. When I go and prove my theorem, so that you understand and you see the proof very transparent, in a transparent manner, it makes sense to think of the process as being a Markov chain with this transition kernel.
Is there a reason why you have written the argument of the exponential function in this way rather than simple minus capital B square?
No, so.
B minus B x, so just capital B E.
Yeah, so put it differently, this thing here, this is just the law of xt when you fix this value to be little xt minus 1. So this is going to be the law of xt. This is a constant. So the law of xt is just normal, mean 0 variance 1 to add this constant. So that means that it's normal, mean this, and variance 1. So I'm just writing down the distribution of this thing. That's all I'm saying. No, because it's nonlinear. Nonlinear. No, it's Navier-Stokes. B is Navier-Stokes. Kalman filter is nothing. Okay? Right. Okay, the observation process. Go on. Sorry? Do I estimate which one? No, it's given. I'm giving it to you. If you, I'm right. So for this, I'm giving it to you. I mean, if you're doing data assimilation, you'll know what it is. I can make it a function of t. Yeah, I can make, there's no problem. Oh, this one is not a function of t. I'm sorry. It's not a function. It used to be a function of t, but I thought I should take it out because, you know, it just makes life a bit more difficult. Right? So this is obviously time homogeneous. It's a time homogeneous, you know, I just keep adding Brownian, normal perturbation. It's homogeneous. Okay, next, the observation process. So the observation process is exactly what I told you it is. It's a function of xt plus, plus noise. So this is, again, a toy model, dimension 1, right? So this is a toy model, the one that everybody in data assimilation is used to and likes, right? Now, the way in which I like to write it down, I would like to say that I'm able to write the distribution of the observation given all the information, all the x's, given the filtration, the signal filtration up to time t, and this has to be, in fact, just given by the signal at the final time. So put it in the language of what Professor Karandikar told you earlier. Xt and yt, they together form a Markov process in discrete time. But the way in which I write it, I want to say, well, yeah, I can describe the probability of y given x in this way, right? As an integral with respect to the Lebesgue measure, and this is the likelihood function. Okay, so I want to describe it in terms of the likelihood function, but as again, if you are used with this one, right, the likelihood function is given by this. Okay, so if you are used with this one, so this is just a translation into this more general language, but the two are equivalent. Okay, so that's the model. Okay, so I've given you now enough about the model to tell you what happens to pi t. So pi t was this conditional, pi t is our nirvana, pi t is the thing that I want to get to, is the conditional distribution of the signal time t given my data. Right, so here I'm saying, you know what, I know all my data, I know that the observation at time 0 is y0, time 1 is y1, and so on, yt at time t is yt. So this is my pi t. And then I have this Bayes recursion. So this tells me how do I get from pi t minus 1 to pi t. Now I'm going to take time and explain to you what is this. Just take it, you know, at face values at the moment. So the recursion is like this. So you start from pi t minus 1. So what's going to happen at this point, the first step will be the equivalent of the forecast. The first step will be pushing forward pi t minus 1, taking the composition between pi t minus 1 and the transition kernel of the signal. So you get something which is called the prediction. This is the prediction step. And then you get the updating step. This is where you bring the new observation in. And the new observation in is you get pi t. And the pi t will be absolutely continuous with respect to pt. And the Radon coding derivative of pi t with respect to pt is going to be given by your likelihood. And then you'll have to normalize. Okay? And I'm going to go into details and explain this even more. And I'll show you how you deduced it. Just take it as it is. Okay? So I'm not going to go into that. And I'm just going to, now, I want to say something about, so, okay, so I've yeah, go on.
The normalization is done with respect to, for instance, the observation distribution of the signal.
No, so this thing, you take the likelihood and you integrate with respect to, is just the probability of that particular observation. Yes. But that observation is fixed. You integrate with respect to the law of the signal. Okay, so data assimilation language. So in data assimilation I'm going to come back to this. So tomorrow I spend a whole half an hour on this page, but go on. Yeah, pi t is my blob. Pi t is that blob. Yes, it's conditional distribution.
No, I'm just trying
Yeah. Okay. So I'm going to tell you tomorrow. I'm going to. For the purpose of today, just take home the fact that there is a very natural reason why we have the forecast and the assimilation and the analysis looked at separately in data assimilation. The reason for that is because the actual posterior distribution evolves in this way. There is a prediction step. Yes, yes. And that's exactly what the point on my 2 slides after. I'm going to tell you, I'm going to put together what filtering people are doing, and I'm going to put together what data assimilation people are doing to just convince you that we do the same thing. It's a bit more. Okay. To get to time t, you think of the prior time t minus 1 as being the posterior time t minus 1. You take the posterior time t minus 1, but you do something to it. You push it along using the signal, and then that's your forecast. And then you say, wait, now I have to embed my observation, and then you do the updating splitting or the analysis. Go. Exactly. Exactly. It's just the way. So this is a function, right? I take a probability measure and multiply it by the function. It's not going to give me a probability measure. It's going to give me a measure. So I have to normalize it to get the probability measure. Happy? Okay. Now, data assimilation language. So what people like. So people say, data assimilation is the process in which we incorporate data into a computer model of a real system. So we try to be very, very vague in here exactly what we want. But what we want, we know what we want. It's just that we cannot get to what we want. So instead of dreaming of that, we try to be very, very realistic. And of course, it has applications in many fields. Particularly, people here are interested in weather and climate forecasts. And that's what I'm saying in here. I'm saying that, again, you have in here you have 2 cycles, 2 steps in getting the estimation from time t minus 1 to time t. And the point is that the one step. So this is written in the other way around. So the first step would be to do a forecast. You start with your assimilation. You start with your estimation at time t minus 1. You do a forecast, and then the forecast is then combined with the next set of next set of observations in the analysis step to get your best estimate, to get your estimate of the signal. Okay, so language is different, but we want to do the same thing, and that's the point that I want to say here. We are dealing with the same problem of merging models, of merging Bayesian, your prior belief with your observations, which are not complete observation. Of course, in data assimilation, it's a more applied subject. There's no theory behind this. And the point that I'm trying to make is that there is a theory that you could use, right? So, mostly data assimilation is interested in solving large-scale problem for large data set. And in filtering, because we have this long history, theoretical history, a history of theoretical development, we know a lot of sort of theoretical behavior, like asymptotic behavior, consistency, and so on. And the hope is that we can get these 2 fields to mesh together so that we learn from one another and help one another in our research. And apparently there's a similar situation happening in context of machine learning and statistics. Okay, so I'm running out of time. Yes. So time. So I'll stop. I'm just gonna show this thing that Sanjay pointed out earlier, that we are looking and we are doing the same thing, and this is what I'm going to do so tomorrow I'm going to start exactly this thing. So I'm going to talk to you, and I'm going to tell you what people that are working in particle approximation in the filtering theory are doing, and then separately I'm going to show you here what people in data assimilation are doing. And I'm hoping to convince you with this page alone that we are doing one and the same thing. So I'm going to stop here, and I'll continue tomorrow. And I'm very glad that I got to page 10. Thank you.